Due presentazioni, una presentazione un po' più lunga dal titolo Magnetic Cooling and Heating, l'effetto Peltier, e viceversa un richiamo anche a un tema che è già stato oggetto di altre presentazioni in questi convegni, che riguarda invece l'ice slurry. Quindi quarto d'ora di tempo, a quarter of an hour. I start with the clock, and please, you have the floor.
Good afternoon, ladies and gentlemen. Usually I make a little sleep after lunch, but I hope that you're awake. And I would like to give a little state of the art of ice slurries. It's not so that I'm actually in ice slurry research so much anymore, and I don't have so many new results, but we wanted to just remember you that this interesting technology exists. Therefore, I will only shortly speak on this. Maybe I skip a few slides, don't be disturbed by this. And my real talk will be afterwards on magnetic refrigeration. I go on directly to the ice slurry production. We had a talk of Sergio Bobo, who was speaking of nanoparticles. These are particles of the diameter, a nanometer is 10 to minus 9 meters, very, very small particles. Then you also don't have so much sedimentation problems. But there are other fluids with larger particles, for example, ice slurries. These are ice particles in water, and the diameter of these particles is of the range of 100 micrometers, 0.1 millimeter. So you can see them by eye. And it gives a slurry, a mushy liquid which can be pumped, and by this it's a very interesting substance for transport of cold. Here you can see a production method. You have a double wall cylinder and a refrigerant which evaporates between the two cylinders. And in the inner part, in here, there's a water additive solution. So you get ice crystals which create on the wall of the inner cylinder, and with a scraper, here it's a rotating cylinder, you scrape away these crystals, they fall into the water, and slowly the concentration of ice crystals increases. I made a little review and saw some nice new principles, also scrapers. There are other methods of creating ice slurry. Here from a review article of last year from Zhang and Ma, you can see especially the scraper on the right bottom looks very nice. It's a screw which naturally is very stable and reliable in the production. The other with the blades, they are blades which are moving up and down in a more linear way, scraping away these articles. Ice slurry in a microscopic picture looks like that. Because of the additive, which can be an alcohol or other substances, there are many different additives, they become rather spherical, and by this naturally also the viscosity is not so high. I'm a little bit proud because I, with a student of mine, Beat Frey, was in the lab in the morning at 4 o'clock, and we saw that the viscosity always changes, and by this we discovered the time behavior. That means that here, for example, little ice particles become smaller and smaller, and on the other hand, larger particles become bigger and bigger. There are several effects like that, maybe in societies where rich people become richer and richer, and the small ones, okay, I go to the next slide. Here we have a laboratory installation which still is running, where we can make a lot of fluid dynamic and heat transfer measurements in our university. That's the specific enthalpy, which is high. You can easily get an 80 kilowatt per meter meter cube, and you see naturally it's related to the transition temperature. Because you have an additive like an alcohol inside, it's a bit lower than 0 degrees Celsius, which is ideal for many refrigeration tasks. You can store ice slurries different manners. The usual way is that in the top where you have a mixer, so you make a homogeneous mixture and you have no problems to pump it out in the secondary refrigeration loop to your maybe display cabinets or other equipment which demands cold. Another idea is that you have heterogeneous storage, that no mixing, and then ice is lighter than water, naturally rises by buoyancy and agglomerates, and concentrates at the top. If the tank is closed, the particles will not freeze together. So you can always separate them again, and in this method that was proposed by me, you can, by a screw pump, take high concentration ice slurry out of the tank, mix it with water from the bottom to your right concentration, and go out with the predefined ice concentration. By this you can save the mixing energy, which is a substantial energy in ice slurry technology. Rheological behavior, it's a Bingham. It has a critical, it has a critical shear stress. That means you need a certain pressure before it starts to flow, and this is related to this rectangular profile on the right side. When the ice concentration goes towards 0, you get here the Poiseuille flow profile of a parabolic velocity profile. You see here also in the flow, when it's flowing, that we have this stratification. By this you have more ice at the top. There it's more viscous, so the velocities will be higher at the bottom, which you see on the left. That was modeled by one of my students in earlier time. Now, to be fast, I already come to the end, but we have to still pronounce here that it's a possibility of supermarket refrigeration, cooling in air conditioning, and it is mainly used in food cooling. I relate to this picture on the right, and there are different special applications in medicine, aeroplane cabin cooling, and so on. So I want to remember you about this very beautiful, interesting, nice, cool secondary refrigerant. Thank you very much. Then next one. Good. That second domain is now really the domain of, I would say, my competence, because I was leading for 10 years the working party of magnetic refrigeration of the International Institute of Refrigeration, being active in this domain with my own research. And a few weeks ago I skipped, and somebody new will take over, but I'm still remaining in this domain with certain investigations. And magnetic refrigeration is a technology which approaches slowly the market, and we have obstacles, and I will speak about something a bit future-oriented, which could be a method to overcome such obstacles. Here I mentioned some of my collaborators. It's a method with nanotechnology, and these are the people from the Nanotechnology Institute of my university who were involved in this work. Table of content, well, we're short in time. I just go on and you see what the content, what the chapters are. For these people who don't know how magnetic refrigeration operates, I have here a little picture which shows very nicely the principle. You see on the underneath, on the left, a magnet. So this creates a magnetic field in the lower part, and in there we have a porous cylinder turning like, probably you know, rotative heat exchangers in air conditioning. So we can flow through with a fluid through the lower part and with another fluid through the upper part, half circle, and we have a part which is not in the magnetic field. If this porous heat exchanger is produced by magnetocaloric material, this material will heat up when it changes, when it goes into the field. It's the field change, it's not the field itself, it's the change of field which makes it heat up. Then this under part, here is hot and the fluid goes through here. A cold fluid coming in heats up because this part, this solid material has heated up. On the other hand, when it goes out, it cools down and the hot fluid becomes cold. So we have all these different mechanisms which are important in a refrigerator to build such a machine. Now, there are obstacles to the frequency of this machine. One is we don't have a fluid with a turbulent motion. Here we have solids, and by this diffusion, that means very slow physical process. That means we need very small distances for the heat transfer. That means porous structures with low characteristic diameters. Here you find that in the paper in the proceedings is a diagram which shows you which frequencies are possible with a material. Here, for example, gadolinium. This is a very well-known magnetocaloric material, which frequencies are possible by heat diffusion. And even more drastic is another one. When you turn a wheel between a hot and a cold side, then if you know rotative heat exchangers from air conditioning, you know that there's a carryover leakage. A fluid particle goes into the cylinder, flies through it. In this time it rotates, and the warm a particle which went in the warm side comes out in the cold side. If you rotate too fast, that means you have a limit here, which also limits the frequency. So all these different prototypes which we are building today have a limit on the frequency of about 2 Hertz. And that's very low, rather low. That means the machines become large and costly. And that's actually the reason why we're not on the market yet. So if we can increase the frequency, you can roughly say double frequency, half size, half magnets. Magnets are expensive. So the volume and mass and costs go down, and we have a better chance to be be better concurrents to conventional refrigeration. So by this, we had the following idea. Instead of turning, we built a machine with layers of magnetocaloric material. On the left-hand side, red in the middle, this layer, that's magnetocaloric material. And we built heat gates to the left and right. And by this, we just can flow by with a cold and a hot flow, maybe countercurrent. And then we just switch open, closed, alternatively on the left and right side. And by this, everything also works, and we don't have these limits in frequency. What are the limits in frequency here? One is the diffusion into the magnetocaloric material. The other one is the frequency of the thermal switch and the magnetocaloric effect itself. But here we speak about milliseconds. So actually, theoretically, we could get up to 1,000 Hertz in these machines. Well, the thermal switch plates would have to be built like that. And the heat gates we have produced with nanotechnology. That means we apply nanowires and build very small Peltier elements which are very, very performant. We have made first prototypes, and just to give you an idea, if we scale up such a nano Peltier element up to a normal Peltier element of 3 millimeters thickness, we would get we would get a temperature difference between the hot and cold side of 750 Kelvin. Naturally, these elements are very thin, and we get 6 Kelvin, which is enough to run this machine, but just that you have an idea of the performance of these Peltier elements. They're very, very performant. Here, that's a device where we have to measure certain things, Seebeck effect, electrical resistance, thermal resistance. I made coefficient of performance calculations. That's naturally a longer. Okay, can you give me 30 seconds? Okay, I'm nearly at the end. You can see I made a comparison between a normal, I already say conventional magnetic refrigerator which is not on the market, and one with such thermal switches. And you can see the red things. I put a red, what's a bit important. I said 10 Hertz instead of 2 Hertz. Mass of magnetocaloric material instead of 380, 64 grams. And a magnet instead of 18 kilo, 4 to 6 kilo. And if this system will work, then the conventional refrigeration slowly could get a problem, because then we are economic. What we also could then be interesting for is naturally for the automobile industry, because then our equipment is not so heavy anymore. And I can tell you there are also 3 automotive companies which have taken up research on this idea. So we're not alone anymore, and that shows probably that the idea is highly interesting. Thank you very much, and sorry for being a little bit too late.